I've been asked to talk about some of the work we've been doing for the last few years in regards to increasing grain protein in wheat. There are 3 years of study by 8 locations that I'm going to discuss. Our 2018 study, which was supported by Sask Wheat and the ministry's ADOPT program, found late season applications of nitrogen could increase grain protein, but it was no better than if all the nitrogen was just applied at seeding. Our 2019 to 2020 studies were solely funded by Sask Wheat. In those studies, we found grain protein could be increased by split applications relative to putting all the nitrogen down at seeding, but it still didn't prove economic. Our studies looked at broadcast or dribble-banded applications of UAN and dissolved urea sprayed at the boot stage and 10 days post-anthesis. Applications late in the season at the boot stage or 7 to 10 days post-anthesis favor increases in protein over yield. If you're trying to maintain yield with a split application, it better occur before the 5-leaf stage, and you'll need some rain to move it into the soil where the roots can access it. When we did broadcast sprays of UAN, we followed the North Dakota recipe to try and minimize fertilizer leaf burn. John Hurd likes to call this the 7-10-20-30 rule. Basically, we apply 7 days after anthesis. We mix 10 gallons of 2800 with 10 gallons of water. We spray below 20 degrees Celsius, and this applies 30 pounds of nitrogen per acre. We also tried to minimize leaf burn by using dissolved urea, which is frequently referred to as melted urea. A few things to note with this approach. Dissolving urea is endothermic, so if you're using cold water, it's only going to make it colder, and this could result in freezing lines. Also, you want to ensure that the urea has less than 1% biuret, otherwise you will burn your crop. Biuret is a byproduct of urea, and most North American products should have less than 1%, but it's best to make sure. Depending on concentration, the use of melted urea may require high water volumes. Let's look at some water volumes required to deliver 30 pounds of nitrogen per acre. If you're using undiluted UAN 2800, then 10 US gallons per acre would be required. This is fine for dribble-banded applications, but it's not really recommended for broadcast applications. When you cut UAN in half with water, you form a product that is 15.7% nitrogen by weight. Note that cutting 2800 in half with water doesn't make 1400. That's because percent nitrogen is based on weight, and a gallon of water weighs less than a gallon of UAN. In our studies, we have melted urea with 14% and 9% nitrogen. Note the large differences in water volume required to deliver 30 pounds of nitrogen per acre. There are a few studies where using melted urea at 9% nitrogen looked really good and was very soft on the crop compared to UAN. But look at the water difference, the water volume difference between UAN at 20 gallons per acre and melted urea at 38.4 gallons per acre. Would UAN be just as soft if applied at 38.4 gallons per acre? I don't know. So all the results I will be discussing today were obtained from our 8 AgriArm locations across Saskatchewan. This figure shows trial results from the 2018 study averaged over 7 locations. The blue bars represent the yield, and the grain protein is represented by the orange squares. The first 2 treatments show increasing side-banded nitrogen from 70 to 100 pounds per acre, and you can see that this has increased the yield and protein of the wheat. Applying 30 pounds of nitrogen to a base rate of 70 pounds of nitrogen also tended to increase yield and significantly increase protein, as seen by the last 3 treatments. On average, protein increased by 0.8% relative to the 70N check. However, late season applications of nitrogen did not significantly increase yield or protein relative to just side-banding the whole 100 pounds of nitrogen per acre at seeding. In other words, it was more inefficient and economic to put all the required nitrogen down at seeding instead of split applying it. If we compare between the methods of split applying nitrogen, you'll notice there is a significant protein boost with broadcast UAN post-anthesis compared to dribble banding, whether it's at the boot stage or post-anthesis. It's hard to say why the broadcast application performed better. Perhaps more nitrogen was absorbed through the leaves, or protein just increased in response to potentially some greater crop injury. However, this wasn't backed up by a lower yield. At any rate, applying all the nitrogen down at seeding was still the better way to go. We also looked at these same treatments applied to a base rate of 100 pounds of nitrogen per acre instead of 70 pounds of nitrogen per acre. The results were very similar, with broadcast spraying providing the highest protein increase, but none of the split applications were really any better than putting all the nitrogen down at seeding. Overall, split applications provided only a 0.6% increase in grain protein relative to the 100-pound nitrogen check. This protein increase was less than the 0.8% increase when we were adding 30 pounds to a base rate of 70 N. This supports the hypothesis that supplemental N is more likely to increase grain protein for a more nitrogen-deficient crop, due to the law of diminishing returns. So the major conclusion from the 2018 study was just put all the nitrogen down at seeding because split applications did not further increase yield or grain protein. In 2019 and 2020, we did a similar study, but this time we included some melted urea in the lineup, as we had heard dissolved urea was softer on the crop. Here is the data combined over 16 site years. The blue bars represent yield, and the yield axis is on the left, which starts at 59 bushels per acre and goes to 67 bushels per acre. The orange dots represent grain protein and are related to the scale on the right, which starts at 13.2% and ends at 14.3%. The first two treatments are the checks of 70 and 100 pounds of nitrogen per acre of side-banded urea without any split applications of nitrogen. You can see wheat yield was increased by 3.2 bushels per acre and grain protein by 0.5% in response to increasing nitrogen. Treatments 3 and 4 are split applications of nitrogen, where 70 pounds of nitrogen per acre as side-banded urea was the base rate, and then 30 pounds of nitrogen per acre was UAN dribble banded at the boot stage. Treatment 4 is straight urea at 28% nitrogen, and treatment 3 is UAN cut in half with water to form 15.7% nitrogen. Compared to just putting all 100 pounds of nitrogen per acre down at seeding, which is treatment 2, dribble band applications of UAN at the boot stage tend to increase protein a little bit, but also tend to result in less yield. Treatments 5 and 9 are all split applications of nitrogen applied 10 days post-anthesis to the base rate of 70 N. Compared to treatment 2, the check, all but one of these treatments resulted in statistically higher grain protein, but all of them also resulted in statistically lower yield. So even though there is more of a protein boost with post-anthesis applications compared to boot stage applications, it still might not be economical due to the greater yield loss. But I'm getting ahead of myself here. Treatments 5 and 6 are dribble band applications of UAN post-anthesis. Treatment 6 is straight urea at 28% nitrogen, and treatment 5 is UAN cut in half with water. Treatment 8 is also UAN cut in half with water. It is applied as a broadcast spray. Cutting UAN in half with water is typically done with broadcast sprays to reduce leaf burn. Again, you'll note that all of these post-anthesis applications of UAN are resulting in higher protein but lower yield compared to treatment 2, where all the N was just side-banded at seeding. Treatments 7 and 9 are dissolved urea. Treatment 7 is dribble banded, and treatment 9 is a broadcast spray. I discovered a calculation error with these dissolved urea treatments and determined only 25 pounds of nitrogen per acre was applied with the dissolved urea instead of matching the 30 pounds of nitrogen per acre applied with the UAN applications. If we go back to the trial data and compare the proteins between dribble-banded and broadcast sprays, you will note the grain protein is a little lower for the dissolved urea compared to the UAN. This likely is the result of differences in applied nitrogen. As stated earlier, we were able to increase grain protein with split applications of nitrogen compared to just putting all the nitrogen down at seeding. However, this also came with a relative yield drop. The greatest increase in grain protein and decrease in yield resulted when split applications occurred post-anthesis compared to the boot stage. For example, dribble banding straight UAN post-anthesis, treatment 6, significantly increased grain protein by 0.32%, but significantly resulted in 4.8 bushels per acre less yield, compared to the side-banded check of 100 pounds of nitrogen, treatment 2. In contrast, dribble banding the same UAN treatment earlier at the boot stage, treatment 4, resulted in a more modest grain protein increase of 0.15%, but a relatively lower yield loss of only 0.8 bushels per acre. The earlier split application of nitrogen at the boot stage may have favored yield over protein. However, the post-anthesis timing may have also increased protein by causing more damage and reducing yield. This hypothesis is somewhat supported by the flag leaf burn ratings. Leaf damage was significantly lower for the boot stage applications, treatments 3 and 4, compared to the remaining post-anthesis timings. Among the post-anthesis timings, broadcast spraying UAN significantly caused the most damage, treatment 8. Broadcast spraying dissolved urea, treatment 9, caused substantially less damage, which supports past research. But the lower rate of nitrogen with the dissolved urea in this study also likely played a role. The dissolved urea also proved to be more gentle on the crop for the dribble band applications, treatments 5 versus 7, but the difference wasn't as great. So in this study, we found we can increase grain protein, but it's coming with a yield penalty. So let's see how the economics worked out. This figure represents the gross returns minus the variable cost of added nitrogen minus the additional cost of applying a split application. This allows for a fair assessment of the relative profitability for each treatment. Gross returns are the product of bushels per acre and price per bushel. A base price of $5.84 per bushel for 12.5% protein wheat was assumed, along with a protein premium or discount of 60 cents per percent per bushel and a nitrogen cost of 50 cents per pound, regardless of the product used. In addition, an extra cost of $5 per acre was added for all split applications. When we look at all the sites combined together, none of the split applications of nitrogen generated as much income as treatment 2, where all the nitrogen was just put down at seeding in the sideband. But what if we looked at high and low yielding sites separately? Producers are more inclined to try split applications of nitrogen to raise protein with a high yield potential crop, because the protein is likely to be low. Perhaps the split applications would be more economical with the higher yielding sites. To test this hypothesis, the top 8 and bottom 8 sites were analyzed separately. The top 8 had an average yield of 78 bushels per acre, with 12.9% grain protein. In contrast, the bottom 8 yielding sites had 51 bushels per acre, with 14.6% grain protein. It makes sense for the protein to be higher with the lower yielding sites, as anything that causes a yield reduction like drought stress, for example, will result in higher protein. The protein and yield responses for the top yielding sites are at the top and the lowest yielding sites are at the bottom. I know it might not be possible to see all the details here, but it's not necessary. What I want you to appreciate is how yield and grain protein responses to treatment between the top and bottom yielding sites are remarkably similar. Yield and protein are responding to increases in nitrogen from 70 to 100 pounds of nitrogen per acre. Split applications of nitrogen at the earlier boot stage are resulting in less yield loss compared to the post-anthesis applications, but are also tending to produce less protein. The exception to this is treatment 4 of the top yielding sites, where dribble banding straight UAN at the boot stage resulted in maintaining high yield and grain protein. Compared to our treatment 2 check, where all the nitrogen is side-banded at seeding, split applications of nitrogen increase protein a little more for the bottom yielding sites, by about 0.08% on average. This might appear a little counterintuitive, as the bottom sites have a higher protein level, which should be harder to increase due to the law of diminishing returns. However, you also have to take into account that 30 pounds of nitrogen can only create so much protein, which would be diluted more with the high-yielding sites and diluted less with the lower-yielding sites. Anyway, let's cut to the chase. Did the economics work out differently between the high and the lower-yielding sites? Here are the economics for the lowest-yielding sites. Again, none of the split applications of nitrogen proved more economic than just side-banding all the nitrogen at seeding. What about the top-yielding sites? Perhaps that will be more economic. After all, producers are more likely to split apply nitrogen for protein when yield potentials are high. Well, there was only one split application that produced higher returns, and that was treatment 4, undiluted UAN dribble banded at boot. That managed to maintain high yields and increase protein. But was all the fuss worth the extra $10 an acre? Remember, these economics are assuming a pretty good protein spread of 60 cents per percent per bushel, which you may or may not be able to count on. So, conclusions. Well, unlike the 2018 study, the 2019 and 2020 studies showed we could increase grain protein compared to putting all the nitrogen down at seeding. Dribble banding or using dissolved urea was softer on the crop compared to broadcast sprays of UAN, although the dissolved urea was only at 25 pounds of nitrogen per acre instead of 30. Split applications post-anthesis increased protein more than boot stage applications, but also reduced yield more. It's counterproductive and didn't prove to be economical. Split applications proved uneconomical whether looking at the high-yielding sites or the low-yielding sites. But wait, there's more. I am going to quickly share with you one of the individual studies we did at Yorkton last year, with the help of ADOPT funding. I really hesitate to share it because some of the results are the opposite of what we were expecting. The objective was to increase crop safety and improve economic returns by spraying at night when it's cooler. So we sprayed in the heat of the day at 25 degrees Celsius, and then we came back later that night to spray the same treatments again at 14 degrees Celsius. All of our split applications were 30 pounds of nitrogen per acre post-anthesis on a base rate of 70 N, even with the dissolved urea this time. And just like before, we compared these split applications to 70 and 100 pounds of nitrogen per acre of side-banded urea. We didn't detect any yield differences between treatments, so I'll jump straight to the protein results because there were a number of significant differences. The red bars are the 70N and 100N side-banded checks for comparison. The split applications were dribble-banded UAN day and night, broadcast sprayed UAN day and night, and broadcast sprays of dissolved urea day and night at N concentrations of 14% and 9% nitrogen. Look how high these grain protein levels are. Keep in mind this experiment was run during the 2020 drought at Yorkton. It was pretty nasty and our yields were half of normal. All I want you to take away from this slide is that every split application of nitrogen increased grain protein relative to 100 pounds of nitrogen of side-banded urea. However, some have done better than others, so let's take a look at the main effects. When averaged across method of application, applying post-anthesis nitrogen during the heat of the day at 25 degrees Celsius significantly resulted in 0.36% more protein compared to applying the nitrogen in the cool of the evening at 14 degrees Celsius. This was not necessarily the expected result. Sometimes applications of post-anthesis nitrogen can increase protein by causing more leaf burn and decreasing yield, but that is not the case here. The daytime spraying was slightly less for yield than the nighttime spraying, but the difference is not large or statistically significant. In addition, the nighttime spraying actually resulted in more leaf burn. Flag leaf burn was rated to be 38.1% for the nighttime spraying, which is significantly more than the 28.2% for the daytime spraying. Now, this leaf damage includes the damage from fertilizer burn plus drought stress, as it's difficult to distinguish between these damages. However, leaf ratings for the check, which weren't sprayed with fertilizer, averaged 17.6%. So any level of damage above 17.6% can be attributed to fertilizer burn. Of course, we weren't expecting the flag leaf burn to be worse for an evening application. Spraying in the cool evening should have resulted in less leaf burn. We were also expecting less leaf burn from the dissolved urea compared to UAN, but that wasn't the case either. These are the main effects for method of post-anthesis application on flag leaf burn, and they're not significantly different from each other. The melted urea does not have lower levels of leaf burn as expected. Overall, broadcast applications of nitrogen increase grain protein relative to a dribble band application of UAN without lowering yield. The superior performance of broadcast applications implies leaf absorption of nitrogen may have played a role in increasing grain protein. This is contentious, as Western Canadian research has found most of the nitrogen from the broadcast applications is washed off leaves and is taken up through root absorption. However, US and European work considers nitrogen absorption through the leaves to be quite significant. Some have suggested that broadcast applications may perform better during a drought because leaves can provide an alternative route for absorption when soils are dry. Perhaps that is what we observed at our location. While we did receive 29 millimeters of rain 5 days after application, the depth of dry soil may have still been a barrier to root uptake. Whatever the reason, dribble-banded nitrogen was less effective than broadcast sprays in this study. While results for nighttime spraying were the opposite of expected in this study, keep in mind this is only one study. I wonder if the drought played a role. Waxy leaves may have provided some protection, and the stomata opening at night may have provided some vulnerability. I don't know. This is all speculation on my part. It would be interesting to do more work with nighttime spraying, but I don't know if I could convince the other Agriarm sites to spray at 2 in the morning.